So in your linear classification notes where you solve your classification problem using least squares, this is an example given, and we will say that linear model with MSC, basically least square solution, will not be able to solve your classification problem if your data is distributed like this, where you have class 1, class 2, class 3 distributed like this. And I have given you the explanation in the notes, but we will discuss that in our tutorial tomorrow. Okay, when I discussed about logistic regression, we will discuss this. Okay, fine. So in today's class, we'll just see some of the mathematical interpretations of your overfitting and underfitting. Suppose if there is a model and you are training a model, and if you get into underfitting and overfitting issues, how to actually mathematically explain that. Okay, fine. So assume that you have a data set. A labeled data set you have. Okay, so if you have labeled data set, assume that this data set given to you just denote with D, and it has been sampled from some true distribution. Okay, there is a distribution giving out these data points for you, and if you see, the distribution can generate infinite number of samples, right? But I am just taking some limited number of samples from that original data set. Okay, so then if I actually see this data set, I can say that my label Y can be a random variable. Okay, suppose if you are doing house cost prediction problem and you can have two houses with same feature. Please don't use mobile phones, I'll just send you out. Please. So if you have like house cost prediction problem, you can have two same features, F1 and F2 both can be same, or like input. Basically your inputs are same, but your outputs can be different. The the house with similar features can have different prices. It can happen, no, in your real world data. Sometimes you may have same features, but with different prices you can have in your data set. Do you agree with that? And maybe let's take one more example. If you are doing rain forecasting, on a particular day, maybe some day 1, you have a feature, this feature may be as having some temperature, humidity and some geographical details in that, and you have to predict whether it will rain on that particular day or not. Okay, so you can have similar feature on day 100, very similar, maybe exactly same feature, but it may rain on day 1 and it might not rain on your day 2, day 100, right? It can happen. You understand the concepts. In the data set there can be some noise, or you may come across some situations where your inputs are same but the labels are different in the data set itself. Okay, so maybe I'll just show you one more example. So if you see this example, okay, so maybe if you just see this example, at a particular x value, if this blue color ones are your labels and your x is your input, and this red color one is what you have fitted using your regression model. Okay, suppose at a particular x, you can see there are like lot of possibilities for your y. Your y is not fixed, it is actually spread out. Okay, in the same way, like I have told you, my X is, my input feature is fixed, but Y is different on 2 different days. In the same way, house cost prediction, you have same feature but different prices. So in such scenarios, what you have to do, you have to basically don't directly interpret your label as a deterministic label. Use some probability notion. Okay, so your Y is a label, is a random variable now. Okay, it has some possibilities, right? So in this rain cost prediction, if you see, for the same X, it has some possibility of 1, it has a possibility of 0 also. Okay, in the same way for your house cost prediction, for this particular X, it has a possibility of Y1 and possibility of Y2. Okay, so you have different possibilities for your label, right? So instead of just defining your label as a deterministic label, let's use probability notion and let's just say that my label follows a distribution P of Y. Okay, or else in other words, P of Y given X. Is this fine? Okay, so this is coming from your data set itself. Okay, so this uncertainty is there in your data set itself. So for your labels, you can find a mean vector using your P of Y given X. This will be your Y. Okay, mean of your Y label. Okay, estimated from your ground truth labels only and the distribution of the labels. Is this fine? Okay, so now again coming back to your data set, like I have told you, I have sampled this data set from a distribution. And I have sampled this from a distribution. Okay, so to do a same task, sometimes I can have like a distribution which can give me some infinite number of samples, right? So but from this distribution, every time I can sample some limited set. My distribution is having the ability to generate infinite number of samples, but at a time I am taking some limited number of samples and I'll give you each set. Maybe let's call this D1 set, D2 set, D3. Like this I can have any number of sets, no? From this total training set, I will subsample and create my training data points. So this is one training data set. One, and this is my training data set 2. Like this I can actually come up with different training data sets from my larger database. If I have, I can subsample and create multiple training data sets, yes, with same number of elements or same number of data points. Okay, so now if I give you this each set to each one of you and if I ask you to fit a machine learning model, then the models will depend on your data points, the training data points to an extent, right? To an extent they will depend on your data points. Okay, so maybe I'll just denote it again. If I have a data set D, okay, you know what is your data set? It's just limited number of samples. So if you have a data set like this and if you are fixing the type of machine learning model, assume that you are doing a classification or regression or neural network, any machine learning model you are fitting on this data. Let's just denote A as the type of your ML algorithm. So this A can be your regression, classification or your neural network or any algorithm, any type of algorithm. Okay, so then I will give you different models. So just assume that the model that you are fitting, so the machine learning model that you are fitting using this data set, this training data set D, let us denote that with HD. Okay, HD, and then HD of X will be your predicted label. Yes. Predicted label, and HD is your machine learning model, and the type of the machine learning model is fixed. Okay. So in this case also, like I have told you, D can be a random variable. Do you agree with that? D can also be a random variable. Do you agree with this? Because my data set can have multiple possibilities. I can see if I am doing rain forecasting only, I can have a data set with certain period and the next period, like that, no? You can have from your total data set. So this D is a subsampled one. In the same way, you can have your D1, D2, like this, no? So can I say D is also a random variable? Can I say that? Yes, because when my training data changes, my model fitting may change. To an extent it may change, right? So I can assume my D also a random variable. So in that case, I will actually see, imagine that I am giving you, I'm giving all of you different Ds, okay? One training data set, basically the D1 to a person and another D2 to some other person, and if they are coming up with different machine learning models, then how many models I'll have with me? I will have these many number of models, machine learning models trained on different training data points. Yes. Starting from HD1 to HDK, I will have these many number of machine learning models with me if I give different combinations of training data points to all of you. Okay, so then I will actually define a mean also, mean over D also. Okay, so then that can become your average value computed over all of the machine learning models fitted. Okay, so then how to define this? Maybe something like P of D into HD into DD, something like this. If D is a random variable, I can actually write like this. Okay, so this is what? This is the average value which you will get by considering all of the machine learning models trained. Is this fine? And all of the machine learning models trained with different training data points. Okay, so yeah, so this is fine. HD we have defined, and we have defined the mean of the label and mean of the predicted. We have defined these two, and now you know what is HD and what is HD hat and what is Y hat. You know these, right? Y is your label and Y hat is the mean of your labels, and HD is your machine learning model and HD hat is your average of all the machine learning models trained on different training data points. Okay, so actually why did we even start this? So in your machine learning model, no, suppose you fix the type of your machine learning model. When I say type, it can be neural network, regression or classification. Once you fit your machine type, you can give you can give X and you can predict Y, right? So in order to actually, in order to describe the quality of your fit or quality of your machine learning, what do you generally compute? If you have to evaluate your machine learning model, the first parameter is your test error, right? Your test error, how is it performing on your test data? So how to define that test error? Suppose you have some data points coming from some p-test. So if this is your test data points, then your test error is, if you actually fix your HD, okay, you have the test data points coming from a small test distribution, that test data points you have, and you have learned a machine learning model with D training data set. Okay, so if you have this, then you can define your test error as if you fix your HD model. Okay, so in this case HD of x minus y, this is your test error. Yes, it's the average error over your test samples, right? So then I told you that D can also be a random variable. So if you want to estimate the quality of type of machine learning model, then what you will do, you will collect all of your HD models that you have fitted, then we will compute the error. Okay, so in this case I fixed HD, but in the next case I will actually randomize my D also. Okay, so maybe I'll just, so this same test error, if I write in terms of what if I just write in terms of integration, what will happen to this? HD of x minus y p of x y dx dy. Is this correct? This is my test error that I have defined here. Yes? Okay. So this, what I am telling, I will not fix my D. I will actually try to compute my test over by taking D also as a random variable. Okay. So in that case, that is called your generalization error or test error. Sorry. Okay, so this will be your generalization error when you take your test data points and you are randomizing your D also. D is your different training data points. Okay, so this error, if I just write it in expectation form again, x, y and D, this becomes your h of HD of x, y whole square. Okay, so this is your test error. Okay, so if you want to tell whether your model, that is your HD, is overfitting or underfitting, you will depend on your test error, right? Yes or no? You will actually depend on your test error, or you will look at your test error and your train error, then you will come to a conclusion whether whether your model is underfitting or overfitting. So mathematically what happens is, this test error, you can decompose your test error into three terms. One is your bias, variance, and the third term is your noise or your irreducible error. Okay, so that decomposition we'll see, and we'll see the significance of each term. Okay, bias, variance and your noise or your irreducible error. So is this fine till now? Is this clear? What I did, I just set up a model with trained on D data set, and I am trying to write the test error for it by randomizing my data points and randomizing my D also, which is my training data points also. Okay, so this is my test error. So this test error we will try to decompose into three terms, like we will actually express this test error as bias plus variance plus noise. Okay, is this fine till now? Okay, so let's so this one, what I will do is, I will just add a HD of x. The mean, I will just add and subtract in this expression. Okay. So what will happen to this? HD of x minus HD hat of x, and again plus HD hat of x minus y whole square. Yes?
If you're already randomizing B, then why do you need a mean of HD?
Why do you?
The model is fixed.
Huh?
HD is fixed. You're changing D, randomly picking up and changing.
Yes.
Then there will be only one model, right?
Why?
It's like you are doing mean of HD because
No, but I am not. See here, in my test error, I am not using the mean model. I am using an individual model. You have multiple models, and yes, you are correct. This HD hat is giving the mean model, but I am not making use of the mean model. Okay, that is a different case. Yes. Yes, 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 yes. See, assume that you have multiple models, but still you are doing this test error computation on a single model. Okay, so because you have to see whether your model that you have fitted is overfitting or not. You, like in the analysis, you will take the help of mean model, but in real time, how will you have a mean model? You will have single data set with you, right? So this is more of a mathematical analysis. You will see what is the conclusion. So HD is what? Just the mean of your predicted value by your models, all of your models. Okay, so this one you just have to use your a plus b whole square and expand. Can you do that? Just take this as a and this as b, this two terms as b, and just do a plus b whole square and expand. Can you do that? So your this term will be yeah. What? Yeah, you can. Plus 2 into HD of x minus HD hat of x. B is what? HD of x minus y. This is fine. I am just using a plus b whole square and expanding. Is this correct? Okay. So just let me take this expectation inside. Please be quiet. Okay, if just take expectation inside and write expectation for all of your terms. This one plus 2 into expectation of x, y, d over your HD of x minus HD of into. Okay, so you have three terms now. I just wrote my generalization or test error, and I am just adding this mean and subtracting, and I am just using a plus b whole square and expanding. So now you have three terms with you. Okay, these three terms you have, no? So I'll just tell you the significance of this first term. Can you see what is that first term computing? It is computing the variance, meaning this HD is a single model that you have fitted using your data set D. When you fixed your data set, you fitted this model, and this is what? This is the average of all of your models. Okay, so how much your model is deviated from your average model, this is captured here. Okay, so this is called variance. We will come back to this again, what it will actually show. So this is called your variance term. So now let's concentrate on these two terms. So from these two terms, let me take out this last one. Can you try proving that? This last term should be equal to 0. Can you try? I'm just taking out my third term. Okay, so this third term, what can happen here? This expectation, if you see, I have expectation over x, y and d. Okay, then if I take this expectation inside and apply to this, here the main randomization happening here over d. Okay, so I can just do this, no? I will just separate and I'll just apply my expectation over d. Is this fine? I have expectation over x comma y comma d and I have this term. I am actually separating expectation over d and expectation over x comma y. So I am keeping my expectation over x comma y outside and taking my expectation over d inside. So if you see, expectation over d will impact only my first term. It will not impact this. Do you agree with that? Because it is a mean. Anyway, it is a mean and it is a fixed label. Okay, it will impact only this. And again, if I take my expectation d again inside, okay, so here expectation over x comma y will be common. This expectation d, if I take it inside, so what is this term? What is this? What is happening to my first term? What is this? What is this? Expectation over d, hd of x. What is this? What is see, here I have hd of x and I am taking expectation over d. What is this? Did we define this already? It is what? hd hat, right? It is hd hat. So now hd hat minus hd hat will become 0. Yes? Then this will become expectation over y, 0 into hd of x minus y. So this term is becoming 0. Yes? Is this clear or should I explain it again? Clear? Fine. So what did I do? I just started with my test error. This is my test error. So my aim is to decompose my generalization error or test error into 3 terms: bias, variance and your noise. Then with that motivation, I'm just doing a small modification, adding this hd hat and subtracting it. So after that I just expanded it using your a plus b whole square, and then I got these 3 terms. One is this, this and this. This third term I have proved that this third term is equals to 0. Okay. So now how many terms you have in your test error? Can you tell me? Can you tell me the terms that are left in your test error? X comma y comma d and hd of x minus so this is my variance first term, and the second term is expectation x y d here I will have a hat. These 2 terms are left now. Yes, these 2 terms are left in my test error, no? Okay, so now this, anyway I have told you that this is variance. And now coming back to this term, let's try to expand this term again. So here what I will do is, I will just add and subtract my y hat. You know what is y hat? Y hat is the mean of your labels. Mean of your labels given that x. At a particular x, you can have different labels also. That might be possible if your data set is noisy. Then noisy or real world. Real world data sets are like that. You can't have a single pixel label all the time. So then this will be y hat minus y. Can you expand in a similar way? Can you expand just using your a plus b whole square? This will be a and this will be your b. Please do that. Please do that. Just write down and just expand. So this term, if I just expand, again I will get 3 terms, a plus b whole square, just 3 terms, hd of x minus y hat of x square. This is my first one, and the second one is y of x minus y whole square, and I have a 2ab term, that is your x. Okay, so this is your expansion. Again, this term will become 0. Can you try and prove that with the same analogy? Please do that quick. You just have to show this third term as a 0 again. With the same logic. We will take the expectations inside and we will try to prove. Please write down and prove, no? Just 2 minutes. So this third term, I am just writing it down again, and I will prove that this is equals to 0. Okay, so what happened to this? I'm just taking this expectation inside. If you see, these two are mean values. Those two are completely mean values. No, so no expectation is not valid. Like you won't get anything if you randomize. It's a fixed value. This is the mean of your predicted values. This is the mean of your ground truth values. Okay, this 2 means no expectation. Here it is a mean. Okay, so here this expectation of y, you can take it here. Yes? Okay, so then I will just write down this as expectation, maybe x comma d, I'll keep it constant. I will take my expectation y here. Yeah, what happens to this term? This is 0. Expectation over y, it is nothing but y hat of x. This is 0. Okay, so now into 0, right? So my third term here also became 0. Okay, so now I am left with these 2 terms. Okay, so these 2 terms are coming from this, and I have a variance already. Shall we write down these 3 terms together? Okay, so the test error right now, I am left with 3 terms, right? So one is the first one coming from your variance, and the second one you expanded and proved that this second term is equals to these 2 terms. Okay, so here okay, so let's just write down x comma y comma d. Okay, so this is your variance, and you have 2 more terms. So these three are the terms actually you have ended up getting these three terms and you are equating your test error to be sum of these three terms. So this one I have told you, this is called your variance and this is your bias. This is your irreducible error. So now can you tell me the significance of each one? Why am I calling this last third term as irreducible error or noise? What is this computing, the third one? Just look at the third one and tell me what is that computing? Is it depending on my model? The third term, is it depending on my model? So what is it doing? At a particular x feature, it is taking the y value, the one label, and it is taking the average of the labels. I told you, no, at a particular x value, you can have multiple possibilities because your real world data sets are noisy and you can have multiple possibilities in the same way for a same feature in your house cost prediction. You can have different prices, no? So these are the possible labels, and if you take average, you will get average of the labels, and if you are taking your one label, maybe a one fixed y from that label average for this x value, then you will get that y, and if you are computing your error, that will give you the noise present in your data set. Do you agree with that? Do you agree with that? The third one will actually estimate the inherent noise present in the data set. Yes or no? Because it is basically taking the average of the labels and a single label and just computing the error between those. Right? Is this fine? Any questions? Yes?
Isn't that the variance of y?
What? Variance of y. Yeah, variance in the labels. Suppose if you have, yeah, I'll just show you. Again, if you just see here, if you have your data points spread out like this, no? Spread out like this, at a particular x, if you see, at this particular x, you have some possibility of labels. You don't have a fixed label in your data point. Data set basically, because I told you an example, no? Data set can be noisy and you can have multiple possibilities. So this multiple possibilities mean you are estimating and you are taking one from this, like basically one, y from it and you are computing the difference. It is like estimating the variance from the ground truth labels. If the variance is too high, then what will happen to my data points? They will be spread out like this. They will be actually having a wider spread, no? Then you can say that your data set is more noisy. Yes or no? Is this clear? The motivation for your third term, is it clear? It is a data set noise or that you can't actually reduce with your model. That is, you don't have any relationship with your data, with your model. Whatever you do, you can't actually reduce your irreducible error or your noise because that is coming from your data set itself. Okay, see if I'm doing rain forecasting, so you have certain feature and you have to predict whether it will rain or not. Okay, so in the real world scenario itself, it is very uncertain whether it will predict, like same features if you have today and tomorrow, it might rain today and it might not rain tomorrow. Okay, so just based on those features, if you learn a machine learning model, how will you predict? If there is uncertainty within the data set, how can you actually overcome that? You can't overcome that, right? So that is your irreducible error or your noise. Is this clear? Fine? Okay, so then let's go back to our two terms and see. So the first one is your variance. It means that this is the average of all the machine learning models fitted, and this is a single machine learning fitted on a particular data set. Okay, so just see, Like you have D1 to D2. D1 to D2, what are these? These are subsampled training data points. Okay, and you have HD1, HD2 and HDK, and you are actually taking the average of this and you have a single model. Okay, so generally average performs better than a single model. Do you agree with that? These data sets are coming from a same distribution, but they are different subsample sets. Okay, and each subsample training set you used for fitting a separate machine learning model. And you have all of your models with you. And if you take average of all of your models, your prediction will be more accurate. Do you agree with that? Than your single model? Yes? Yes sir, no? The single model basically may not perform like your average of all of your models. So if you just compute the difference between these two, no, what you will get? You will actually get how far your model is, your single model is from your average of your models or more generic model. So this you call it more generic or more accurate. So how far your single model is from your average model, that will be captured in your variance. Okay, so if the variance is too high, what will happen? The single model that you are estimating with this particular training set, it is far from your average. It means that this particular model is over specializing on D2. Can I say that? If it is over specialized on D2, then it will be far away from your average model. So then in that case, variance will be high. Okay. So high variance indicates what? High variance indicates what? Overfitting. It is over specializing on this D2. That's why it is far away from your average. Okay. Overfitting can happen if your variance is too high. Okay, is this fine? The variance term is clear? Okay, so now come back to our the second term, that is your bias term. You have to tell me what is this actually. Just look at this and tell me what is this. What is this? I have average predicted output. I have average ground truth. This is average ground truth, right? Ground truth or my label. This is my average predicted. So what is my bias term doing? What is my bias term doing? It is basically computing the error between predicted and your ground truth, right? So can I say in a way this is like a training error? Can I say this as my training error of my average model? Can I say that? This is like a training error only. No, it's a predicted value, it's a ground truth value. And I am taking the difference between predicted and the ground truth. And I am actually taking the average predicted, average ground truth and computing the error. So this is like your training error. Okay. So if your bias is high, it means that your training error is high. So what is the scenario? What can you conclude about this scenario where bias is high? What? Can I say this as my underfitting scenario? Okay, maybe I'll just show you the plots again. So if my training error is too high, then I can say this is my training error too high scenario, right? Blue color one is your training error. So this is your underfitting scenario. Yes? Where your training error, basically the predicted value is not matching your ground truth value. So this is computed in your bias term. Okay, so now you have your test error. Test error is equals to variance plus bias plus your noise. Okay, if your variance is too high, you may get into overfitting issues. If your bias is too high, it means that your training error itself is high. Your model is very simple maybe. So you may get into underfitting. And whatever you do, you can't reduce your irreducible noise. Right? So if you have to actually minimize your test error, you have to balance between your bias and variance. Do you agree with that? If you have to reduce your test error, basically you have to balance between your bias and your variance. Bias is actually telling you whether your model is underfitting or not. Variance is telling you whether your model is getting into overfitting or not. Okay, let's see the clear analysis maybe in next class. But for now, this is called your bias variance trade-off. If you actually see any machine learning textbook, no, when they explain overfitting and underfitting, you may come across this term, bias variance trade-off. Okay, so we'll see the analysis maybe tomorrow. Just go through the derivation once before you come to the next class. Okay, thank you. Any doubts? Okay, thank you.